Neuroscience Education Workshop. My name's Andrew Zalesky, and I'll be presenting on Connectome statistics. I'm going to begin with introduction to network thresholding. I'll then move on to null models, and finally I'll wrap up with comparing connectomes. I'll particularly look at connectome inference and connectome prediction. All these slides can be downloaded from the website that I've shown here on the first slide. And if you have any questions, please don't hesitate to send through an email. So, connectome thresholding. What is thresholding? Well, thresholding is performed immediately after the connectome has been mapped, whether it be a structural or a functional network. And it simply involves removing the weakest connections from the network. And this can be done in an incremental way, and it's governed by, and it continues until we've reached our desired connection density. It's important to emphasize that thresholding is not essential, but it can help in terms of improving connectome visualization, reducing false positives so that the weakest connections are more likely to be the connections that are spurious. It can simplify the interpretation and computation of some graph analyses, particularly when we're computing null networks. For high-dimensional networks, so when we're mapping networks at the level of vertices or voxels, it can reduce storage burden. And finally, some recent work by Buchanan and colleagues has shown that thresholding can in fact strengthen associations with age and behavior. Now, the counter-argument is, you might want to consider, why not to threshold? And as I said, thresholding is not an essential step. And some work by Sivia and colleagues has shown that, first of all, the thresholding cutoff value is arbitrary. So should we threshold at 10%, 20%, 30%? It's not clear. It's generally an arbitrary choice. Moreover, the argument that Sivia and colleagues make is that the connections that we throw away with thresholding are generally the weakest connections. And so it turns out that whether or not we throw these connections away, their overall influence on network measures, such as path length in this example, is probably negligible. So they contend that, well, what's the point of including a thresholding step if the overall consequence is minimal? There is one further step that can be done. Once we've thresholded our network, we can also then go on and binarize the network. And this is where we're only interested in knowing whether a connection is present or absent between a pair of nodes. We throw away the information about connectivity strength, whether that be functional, the correlation coefficient, or the streamline count. The disadvantage of binarization is that this variation in connectivity strength is most likely to be informative and biologically meaningful. We see a rich variation across pairs of regions in connection strength. However, the counter-argument is that it's probably likely that some of this variation is due to noise or methodological confounds, and therefore by binarizing connections, we potentially remove some of those confounds. So here's a conceptual example of thresholding. We start here. This network has three types of connections: weak, moderate, and strong. And so in the first step, our network comprises connection density of 26%. Connection density is just the actual number of connections in our network divided by the total possible number of connections. So in the first step here, we eliminate the weakest connections, and this reduces the connection density to 20%. And then we can go one step further and also eliminate not only the weak connections, but also the moderate ones. And this further reduces the connection density down to 30% in this example. But note here that one of the nodes becomes fragmented from the network. And this can happen if we threshold too severely. And this fragmented node can be problematic for some graph analyses. There are two broad classes of thresholding methods. The one that I've shown here from the top, which is referred to as density thresholding, is where we prescribe a desired connection density, in this case 20%, and we remove the weakest connections until we achieve our desired connection density. And this is achieved with the brain connectivity toolbox function called threshold proportional. The other kind of thresholding method is weight-based thresholding. And in this case, rather than prescribing a connection density, we prescribe a minimum weight. And any connection that's below that minimum weight is discarded. So in this case, we say any connection, an example that I've shown here, any connection that comprises fewer than 3 streamlines is discarded. So we see that the connection here between comprising 2 streamlines and 1 streamline is removed. The crucial thing to note here is that there's a one-to-one correspondence between density and weight-based threshold. For any given density, I can tell you the equivalent weight that will achieve that density, and it goes the opposite way as well. So you might argue then, well, what's the point of if there's a one-to-one correspondence? Why should we have these 2 different thresholding methods? And this difference comes about when we look at groups of subjects. And in this case, in this example, I've shown 2 connectomes, 2 networks, Jack and Alice, and we see that Jack's connectome comprises a greater number of strong connections. These are the edges, the thicker edges that I've shown in the network. Now, if we threshold in such a way that we discard the weak and the moderate connections, we see that Jack's thresholded network comprises a greater number of connections compared to Alice's network, to Alice's thresholded network. So then if we go on and do subsequent graph analysis, network analyses on these thresholded connectomes, any differences, for example, in path length or clustering coefficient between Jack and Alice are most likely driven by this confound in connection density, namely the confound in the different number of connections. So you might say, well, given this confound, maybe we should be using density-based thresholding. And by definition, density-based thresholding ensures that both Jack and Alice's thresholded network comprise exactly the same connection density, in other words, the same number of connections, 7 connections in both cases. But the disadvantage here is that in the case of Alice, to get Alice's network to 20%, we've had to admit some of the connections with moderate strength. And these connections are more likely to be spurious. So we're kind of adding in connections to make up the numbers, but these spurious connections can add noise and a different kind of confound to the network. This difference between weight and density-based thresholding comes up in patient control comparisons. And so this is an example in schizophrenia. In general, what we see in schizophrenia, functional connectivity is weaker in patients compared to healthy controls. So if we apply a weight-based threshold, so if we remove functional connections with a correlation below 0.2, we see that there's a striking difference in connection density between the patient and the healthy control, 53 by 75. And this would confound any subsequent network analyses, potentially confound. If we use density thresholding, sure, we guarantee that there's a matching in the connection density, in the total number of connections between the patient and the control, but we've had to lower the bar. We've had to lower the bar on the minimum connection weight for the patient. So we have to drop that down to 0.31. And so the additional connections that we're adding in could potentially be spurious connections, false positives, which can add noise to the thresholded connectome. Another key consideration is the choice of threshold. Should we threshold at 5%, 10%, 20%? It's not clear. And so to get around the dependency of threshold, it's recommended to evaluate, to perform the analysis, the network analysis across a range of thresholds, and then perform statistics on the area under the curve. So in this case, we've mapped path length as a function of connection density and then computed the area under that curve. This also relates to topological data analysis. Check out the work by Anne Sizemore. There is also an approach called multi-threshold permutation correction, and this is where we look, it's also evaluating a range of thresholds and looking for a continuous range at which we can reject a null hypothesis. This is work by Drake Smith and colleagues. A more recent thresholding approach is referred to as consensus thresholding. This is where we rather than thresholding individuals, we look for a consensus across a group of individuals. And in this case, we see that in Alice's network, if we look at this particular pair of connection, connection here, we see that that's a weak connection, but it survives in the network. And the reason why it survives is because Bob and Jack, that connection is actually strong. So we need that there be a moderate or strong connection in 2 of the 3 individuals for the connection to survive. In what I've discussed so far, thresholding has been performed on connectivity strength. An alternative approach is to cast thresholding in a statistical framework. In the case of functional connectivity, we can convert the correlation coefficient to a z-score, and then that z-score can be we can convert that to a p-value, and thresholding can be performed on the p-values in a statistically principled way. The tricky thing here is that due to autocorrelation in the ball time series, the degrees of freedom are often inflated, and therefore our p-values are optimistic. Afayuni and colleagues have proposed an adjusted z-score where they estimate a more realistic degrees of freedom and yield a more accurate p-values. Check out the work if you're interested in thresholding p-values. Another approach is local thresholding. So what I've discussed here are a global thresholding methods where we apply one global threshold across the whole network. There can, however, be locales within a network where a connection is strong relative to its neighboring connections, but within the global network it's weak, and we might want to maintain those connections. And so there's approaches such as the disparity filter that can allow us to do this. The other key concern is if we threshold too severely, nodes can fragment. So there's approaches such as the minimum spanning tree, which will guarantee against node fragmentation. So in summary, I've introduced connectome thresholding. I've mentioned that it's not an essential step, but it can alleviate false positives, ease the computational burden, help with connectome visualization and interpretation of some measures. I discussed the 2 most common thresholding methods, those being weight and density thresholding. I also highlighted the importance of evaluating a range of thresholds. And so if you're interested in actually doing this on your own data, the BCT functions for weight and density thresholding are shown here.